Okay, so for this lesson, we're going to go over the topic of symmetry. What does it mean for something to be symmetrical? Basically, depending on the line that you pass through it, like it can be a dotted line, it can be imaginary, it can be an axis, like the x and y axis, which is what we're dealing with. Anything can be symmetrical if given the right conditions. So, for example, something like this. Okay, I can do better than that. All right, something like this, like a parabola. Um, as you can see, the y-axis is actually what's cutting this thing. If you were to run a line through the y-axis, right, would it cut it in half? Yes, absolutely. This region over here is the same amount as this region over here. It looks like a mirror image, like it can fold into itself. So this particular graph, what have was called y-axis symmetry. Look at the x-axis. Yes, it's touching the x-axis, but the x-axis is not cutting it in half, not at all. So this particular graph, and here's the equation: y is equal to x squared. Let me make sure you guys can even see that. Yeah, you can see it. Okay. Yeah. Mathematically, it can be, it can be solved as well. So how do we solve it mathematically? That's why I have this table here. So I created it myself. Up here, SYM stands for sim. And as you can see, there's y-axis symmetry, which means the y-axis cuts it in half. There's x-axis symmetry, and there's origin symmetry. Origin symmetry is it's a little different, but it's like you're gonna focus on, I would say, this point here. Now I'm gonna give you some examples as well. Um, for all the symmetries, you're gonna substitute different things, and be careful. Like the world of mathematics is so confusing as it is, right? If you're testing for y-axis symmetry, you want to substitute a negative x into your equation. And if that equation, once you simplify, is still the same as the original equation, and don't worry, we're going to go over these two examples. If it stays the same, it's going to have that particular symmetry that you were testing for. So for the x-axis symmetry, you substitute negative y. For y-axis symmetry, you substitute negative x. And for origin symmetry, you're going to substitute both negative x and negative y. And yes, you're going to see if the equation will change after doing both of them. And if it doesn't change, if it simplifies to be exactly the same as your original, then it will have origin symmetry. So I gave you a y-axis symmetry. Let me give you an example of x-axis symmetry. So imagine if um, let's say I'm doing something like this, right? That looks like a weird shape. But is the x-axis cutting it in half perfectly? Yes, it is. If you were to fold this top portion up and fold it along this way, it looks like a mirror image. It's like this thing is looking at this thing, and the x-axis is the mirror. So that particular thing will have x-axis symmetry. Now, for something like, so this is y-axis symmetry, and this is x-axis symmetry. What about origin symmetry? How would that look like? Origin symmetry can be a little tricky, but here's an example. So imagine you have something like this. Does this look familiar? This is the graph of y is equal to x to the third power, x cubed. So here's how I go about it. I think of running a dotted line straight through the origin, maybe going that way. And if you can, if every point over here corresponds to another point up here, and it looks like you can jump across the corner here, this is 0, 0. That's your origin. If you can jump across from here to here, will it meet? Would it be a mirror image? Yes, it will. It's like an inverted mirror type of thing going on. Um, I give you another example for origin symmetry because origin symmetry is just so so weird. If I draw like a football type thing, or some kind of French bread or something like that, and I run a dotted line. With that diagonal dotted line, cut it in half. Yes, absolutely. So this particular oblong shape, I don't know, the oval shape, that will have origin symmetry. So yeah, we did x-axis, y-axis, origin. And what about all of the above? There are definitely cases where you can have symmetry for each and every possibility for x, y-axis, and origin. And I think the best example I can make is like something that's like a perfect circle. The y-axis cuts it in half, the x-axis cuts it in half, and the origin cuts it in half. So circles are perfect, right? Like it's the most ideal shape to store energy. It's the best shape that a pizza can be in. uh, yeah. So yes, based on the test, based on the graphs, you can have all three symmetries. If it's a circle and it's right in the middle like that, or you best believe, absolutely. So let's mathematically go over how do we know that something has x, y axis or origin symmetry. Okay, so let's do it. So let's go ahead and test for y-axis symmetry for this number here, 15x to the fourth plus 28, y to the fourth equals 63. Um, let's test for y-axis symmetry. So to test for y-axis symmetry, you want to substitute negative x for every time you see an x. So all you do is put 15, make an open parentheses like this, put a negative x in there, plus 28. Remember, we're not testing the x-axis symmetry, so do not change your y. Just leave it like it is. And let's just take a second to evaluate this for a second. Okay. Nothing happened here, but take a look at this. If you take a negative number or a negative variable and you raise it to an even exponent, you can imagine, you imagine this. This is negative x times itself 4 times, right? An even number of negatives is going to be a positive. So a negative times a negative is a positive, times another negative is a negative, times another negative is a positive again. So this is a positive x to the, how many x's we have? 1, 2, 3, 4. Positive x to the fourth power. So looking at it that way, we know we're going to end up with a positive x to the fourth again. And isn't that what we had in the beginning? So that'll be 15. You can take this out of the parentheses. We know it's going to equate to x to the fourth plus 28 y fourth equals 63. And this is where you ask yourself, okay, is this the same as our original? Yes, it is. Number for number, letter for letter, tongue tie. It's been a long day. Anyway, yes, letter for letter, variable for variable, whatever. Yeah, it's the same. So guess what? We just found out that this equation definitely has y-axis symmetry. So I'm just going to put a check mark there. Now let's try for x-axis symmetry. So we're going to substitute negative y every time we see a y. And let's save on some time here. If you put a negative y in there, like substitute a negative y, and you're going to multiply them 4 times together. So negative y times negative y times negative y times negative y. It's going to be the same result when we plug negative x in there, right? So it's going to end up being positive again. So that's going to have x-axis symmetry. So, looking at the x-axis, I'm not sure exactly how this graph looks like here, but I know for a fact because of the math and because we substitute these, these negative variables in there, it ended up being the same because it's an even exponent. If it was an odd exponent, like to the first, third, fifth, seventh power, it will not stay the same because an odd number of negatives, remember if you have like negative 1 times negative 1 times negative 1, let's do 5 negative ones just to prove a point. A negative times a negative is a positive. A positive times a negative is a negative. Then it turns positive again, then negative again. So that'll be negative 1. And that will not be the same as your original. So it has x-axis. It has y-axis. Just for kicks, we can go ahead and test origin by substituting negative x and negative y at the same time. So that'll be 15. Oh, wrong color. So that'll be 15 we're putting a negative x in there, plus 28, we're putting a negative y in there, equals 63. So remember, an even number of negatives will be positive, so it can come out of the parentheses now. Plus, I kind of ruined the moment here. I ruined the fun, the surprise. Anyway, an even number of negatives will still be positive. Now, this is where we judge. Is this the same as our original? Yes, it is. Every term is exactly the same. So, and we just did origin because we tested both negative x and negative y. So in this case, this particular equation here will have y-axis symmetry, x-axis symmetry, and origin symmetry. So that answer right there would be all of the above, basically. If you have a graphing calculator, you can type it in and see how it looks like. Maybe I'll make another video on it some other time. Okay, let's go ahead and do y equals 6s to the third power. So let's go ahead and try for y-axis symmetry. So we're trying to find y-axis symmetry. So we're going to substitute negative x every time we see an x. So we have y is equal to 6, open parentheses, negative x to the third power. So this is an odd number of negatives. This is a negative times a negative times a negative, which is still negative. So this is y is equal to negative 6x to the third. So remember, when you have 6 times negative x to the third, you can bring the negative in front because it's multiplying. Now, is this the same as this? No, it is not. So it will not have x-axis symmetry. I'm sorry, y-axis symmetry. What about, what about x-axis symmetry? We're going to substitute negative y this time. So you can imagine a parentheses going around your y. Every time I substitute any number into any variable or any variable into itself, whenever you're replacing a variable, it'll be a good practice to put a parentheses around it. Okay, this is safe to come out of the parentheses. Isn't that just negative y? Now, if you wasn't too certain, yeah, we have 6x to the third power. They're both positive 6x to the third power, right? But these are not the same. So we don't really have to do much to here. Yeah, we just found out that substituting negative y, which means we're looking for x-axis symmetry, we just found out that it does not have x-axis symmetry. So now, I don't want you to think that just because it doesn't have y-axis symmetry or x-axis symmetry that it doesn't have origin, because yeah, there's a good chance that it does. So we're going to take the same original equation. We're going to do both negative x and negative y and see what we get. So that's negative y is equal to 6, open parentheses, negative x, close parentheses, to the third power. Okay, the negative y is free to come out. There's nothing to evaluate, no exponents, so it can come out. This, however, this is negative x times itself times itself. That's 3 negative x's, so negative x times negative x times negative x is still negative 6x to the third power, just like what we got up here a little while ago. And now, we would like, is very close to this, right? Now, the way I look at it, focus on just one side. This is a positive y, this is a negative y. To get rid of a negative coefficient, you just multiply everything by -1 or divide everything by -1. You get the same result, whether you choose to multiply or divide by -1. Then check this out. We get y is equal to 6x to the third power. Isn't that exactly like the original we have there? Yes, so in this case, this particular equation will have origin symmetry. And that is it for symmetry. Yeah, so mathematics is kind of tricky, right? If you're trying to find out if something has y-axis symmetry, you're going to substitute the opposite letter, negative x. If you're looking for x-axis symmetry, you substitute its opposite letter, which is negative y. For origin, you do both at the same time. If you get a negative somewhere, maybe you can divide both sides by -1 to see if it'll equal out to the original. You want to try to make this look like the original as much as you can. And sometimes it relies on you multiplying or dividing everything by -1, like changing all the signs. All right, that is it. Thank you for watching.